In this video, we'll talk about Euler's method and the errors we get from doing this numerical approximation. So in general, the more steps you take with Euler's method and the farther out you try to push the solution to later t values, the further away you get from the solution. However, this is not necessarily always the case. It's the case that we have less of a guarantee of how close we're going to be, but it's not necessarily means we are not going to be very close. Because this is based on tangent line approximation, so the errors in Euler's method are the same as that for tangent line approximation, in that the farther you go away from the base point, the less guarantee you have that you're definitely going to be close to the curve at your next point. You can obviously remedy this by taking smaller steps and using more steps to get there, but that takes more runtime and more code development to make that happen. However, it doesn't mean that you're always farther away the further out you go in the process. There's a couple examples to see sort of what happens here. So if we consider two different differential equations, y prime minus y equals 2 and y prime plus y equals 2, we can solve these analytically using our first order linear methods. And we get that for this one, our solution y of t is minus 2 plus c times e to the t. And for the second one here, we get that y of t is 2 plus c e to the minus t. Now you can think about Euler's method as you take these steps, right? Every step gets you off of the solution curve you're supposed to be on. So you're supposed to be on a curve for a particular value of c, right? And that's chosen by your initial value. So that initial value determines the value of c that you should be on for the solution. Now you take one step with Euler's method, and that is going to give you to a new point that isn't quite right. It's not quite on the right curve, so it doesn't have the same value of c. Let's modify this value of c by some amount. And assuming that things are done, relatively reasonably, this new value of c will be close to the old value, but it's different. And so every step of this process picks a new value of c as it goes. So you're getting more and more different selections of values of c as you step through the problem. You're following similar solution curves, but with different values of c. And depending on the general solution, will determine how this changing c affects the outcome. So for this case, we had two different solutions. For the first equation, y of t was negative 2 plus c e to the t, and the other one was y of t is 2 plus c e to the minus t. Now if we notice the further we go out in t, what's going to happen? Well, if I have a different value of c over here, this gets multiplied by e to the t, so it gets big as t gets bigger. So the changing c on this first one is going to cause some problems. Mainly because in this case, that solution is not actually stable. Things are going away from minus 2. So if I change the value of c, I'm going to get a very different value going forward because it's multiplied by a bigger and bigger function. However, for the second example, this is multiplying by e to the minus t, and that's getting smaller. So here, if I'm off on my value of c, it's not really going to affect too much. Because in this case, the part that c is affecting sort of goes away. And so it's not really going to affect the solution that I get as I go forward, because that part's going to vanish. I'm going to just approach 2 anyway. So even though we have less of a guarantee of how close we can be to the actual solution at that point, because we have a sort of stable solution that's funneling in towards a value, we're going to still be close no matter what we do with this Euler's method. That's just sort of an idea of what actually happens when you're doing Euler's method, how it changes your actual solution, as well as why it may or may not actually affect your outcomes at the end when you do this process for a long period of time.